My name is Johannes Diller. I am a research assistant at the chair of metal structures at the Technical University of Munich. And today I would like to present to you the topic about laser powder bed fused 316L versus hot rolled 316L, a comparison of cyclic plastic material behavior. So why is this important, or why is it interesting? To talk about that, I would like to show you this with the tensile properties of 316L of the two different manufacturing processes. From now on, I will call laser powder bed fusion PBF-LB. It's not really much shorter, but at least a little bit, so we can save some time. Take a look at the graph here. We can see that the mechanical properties differ quite a lot. For example, the yield strength of the hot roll 316L is 245 compared to 455, so it's a great difference. The ultimate tensile strength does not vary that much, but the elongation and fracture, of course, is also quite a bit different. But what's most important here is that we can see there is a difference in the strengthening mechanisms. Here we have a plateau of the plastic zone, and here a hardening effect occurs during the tensile testing of the hot roll specimen. So to investigate this a little bit further, or to take a look at the cyclic plastic material behavior, I will first give a little introduction to the additive manufacturing process, namely laser powder bed fusion. Most of you guys know it probably, but still I will explain a little bit. Then I will come to the experimental setup, followed by the results and the discussion. And in the end, I will give a conclusion and a small outlook, what should be done even further. So this is basically a build chamber of the laser powder bed fusion machine. We have a hermetically sealed build chamber filled with argon. We've got our recoater here, our powder storage, the build platform, and the overflow container. Here on the top, we've got our laser with a mirror, guiding the laser beam into the right area, and the build platform and the head theta lens is focusing the beam to the right dimension, usually up to 100 to 200 micrometers in diameter. So let's perform a coating process. Now we apply a small layer of metal powder on the build platform, usually about 40 to 20 to 40 micrometers, depending on the machine you're using. And then we're performing the melting process. So this process is being repeated until the part is finished, meaning that the recoater is going to the right, powder storage is going up, build platform and overflow container are going down, and another layer is being put on, and the laser is doing this until the part is finished. So what's important here is that we have a high energy density or a high energy input in a very small area, meaning that we have a fast liquefaction and a small solidification, or very high cooling rate, I would say, of up to 40 Kelvin per microsecond, depending on the literature. Great differences in between that. So let's take a look at the cooling rate, or basically at this graph here on the right side. You can see in the x-axis the interface growth rate and the temperature gradient G. And the product of these two is the cooling rate. And for PBF-LB we have a very high cooling rate, resulting in a smaller grain size, because the product of these two, as I said before, defines the cell size. Compared to that, the hot roll 316L has a lower cooling rate and therefore also a larger grain size. And to put that into respect to the yield strength, we can see that we can use the Hall-Petch relationship, meaning that with decreasing cell size, the yield strength increases, and this is also called grain boundary strengthening, which has a nice side effect that we have nearly the same elongation and fracture, meaning that it doesn't become very brittle. So let's get to the experimental setup. We conducted strain control fatigue testing with a strain ratio of R equals -1, meaning we are in the compression and the tension range. We applied the strain rate of 0.004 per second, and we applied different strain amplitudes varying from 0.5 to up to 3% in tension and compression, with a step of 0.5%. We also conducted tensile testing, and I showed you the results at the beginning already, so no need to show that further on. And we also used this specimen geometry, or at least this area in the middle here, to investigate the microstructure before loading. We also investigated it afterward loading, but I will get to this later. The applied laser parameters you can see here, resulting in an energy density of roughly 66 joule per cubic millimeters. And in the micro range, we investigated the crystallite size or cell size, the microtwin formation, the orientation, and the phase composition. And for the overall components, we investigated the ferrite content and the chemical composition. So let's get to the microstructure before loading. And as we can see, for the PBF-LB manufactured 316L, we have, as expected, an anisotropic microstructure with very fine subgrain size, varying between 400 to 600 nanometers. Also no initial twinning was visible, and we have a high nickel content, or the chemical composition reveals a high nickel content of 12%, which is at the upper spectrum for 316L. Just keep that in mind for the next slide. We also measured no ferrite content at all in the overall component. The microstructure of the hot rolled 316L, however, looks completely different. Here we have an isotropic microstructure. We have a large grain size of up to 192 micrometers diameter. We also saw some twinning here, and also here in the bottom. We have a low nickel content, meaning we are at 10% or 10.02%, which is at the lower end of the spectrum for 316L. But this is what you get when you buy some 316L at the store. It varies a bit, and they are allowed to do that in the end. The ferrite content here was a bit higher. We had, or at least we measured a little bit of ferrite of 0.3%. Also, if you apply it to the Scheffler diagram, we are a bit more in the area where we have some ferrite. So let's get to the strain control fatigue testing results. And here we compared the number of cycles versus the maximum engineering stress in megapascal. On the left side you can see the PBF-LB process, and on the right side you can see the hot roll process. The different colors indicate the different strain amplitudes, which you can see here in the legend. So what we could see here for the PBF-LB process is that we have high initial stresses, followed by an, I would call it, initial hardening, but the main strengthening mechanism, or weakening in this case, was a softening behavior. Only from 2.5% strain amplitude we saw a little bit of secondary hardening. You could also call the first effect of primary hardening, but I think it's more of a softening overall, so I call it primary softening behavior. On the hot roll 316L, however, it is looking completely different. We have low initial stresses, and we have a primary hardening behavior overall. Also, stresses of up to 700 megapascal were generated during the testing. Take a look at this from a different perspective. We compared the different strain amplitudes at each of every graph, and we normalized the number of cycles to have a better comparison between the two processes. So, yeah, one equals the end of each of the fatigue life in the end. So in this case, yellow color is PBF-LBM, and the blue color is hot roll 316L. And for the hot roll, we can basically say that with increasing strain amplitude, we have also an increasing hardening rate, meaning that at 0.5%, no hardening for the hot roll 316L, nearly no hardening was observed. For 1% strain amplitude, we manage both processes actually are meeting each other at the end of the fatigue life. But from 1.5% strain amplitude onwards, you can see a clear hardening behavior of the hot roll 316L, exceeding the stresses by a lot from the PBF-LBM manufactured 316L. So let's take a look at the microstructure after 2.5% strain amplitude, because I think these are the most interesting ones. There we did a longitudinal cut from the fracture surface, the bottom or the top, which you can see here in the middle. We embedded it in resin, polished it, and etched it in the end with Pera-H2 etchant, so we can see the different grains. And here we can see small slip ends inside a large grain of the PBF-LBM manufactured 316L. However, the subgrains, I would call them, they weren't really affected, but I will get to that later on. Here we measured a ferrite or martensite content of 0.31%, and we also saw some twinning. So we used the ferrite scope to measure the ferrite or martensite content, and the problem there is that it cannot distinguish between ferrite or martensite, so that's why I'm saying it could be both, but I guess because we have only austenite, or mainly austenite, we have an austenite to martensite phase transformation during the induced plasticity at the end. If we take a look at the hot roll 316L, we have a much higher ferrite or martensite content of 11.5%. And here we can say that there is a possible martensite transformation. To investigate this a bit further, we did some EBSD measurements, measuring the orientation in between 58 and 62 degrees, because this is the area where mainly the twinning of austenitic stainless steels is occurring. And here we measured, at least for this small picture, but I will get to that later as well, a small amount of twins of 2.2%. Again, this is 2.5% strain amplitude, so this is deformed. So we have a little bit of mechanical twinning, which coincides with the results I showed earlier, that we have a very small amount of secondary hardening close before the end of the fatigue life. For the hot roll 316L, however, we can see a much larger twin fraction of 10.2%, so we have a mechanical twinning. But we also investigated the crystal lattice structure with a EBSD measurement, and here we can see that we have also 11.5% martensite. For PBF-LB we couldn't find any difference, even though there was a small amount of ferrite or martensite measured with a ferrite score. I guess it is because only, and I will get to the results of that later, only martensite can only grow inside a grain. Because of that, since we have so small grains in there, we cannot really measure it. At least our machine couldn't measure it. Probably there might be some, but we can discuss it later on. So last but not least, I will talk about the strain controlled fatigue testing results in terms of the fatigue life. And here the strain amplitude and the number of cycles is compared. For the curve fit, we use the plastic part of the Mensinger coffin approach, and we can clearly see that the PBF-LB manufactured 316L actually has a better fatigue life compared to the hot roll one. I need to say that we polished the surface of both samples before testing, obviously, to have the same surface roughness at the end. I mean, the professor said earlier that this is also a big influence. We're also investigating that, but I'm not talking about that today. So to get to the final conclusion, and I hope I still have some time, the PBF-LB has higher initial maximum stresses, followed by a softening behavior. Hot roll 316L has lower initial maximum stresses, followed by hardening behavior. And PBF-LB 316L basically has a higher fatigue life compared to hot roll 316L, at least for my results. I mean, I need to do more to actually state that properly. As I said before, martensite can grow only inside a grain, and therefore we are thinking that no too little martensite transformation at the PBF-LB manufactured 316L occurs due to the small crystallite size. So we probably maybe have twinning-induced plasticity at the 2.5% strain amplitude. However, we could see the martensite transformation at the hot roll 316L due to the larger crystallite size, and therefore the effect might be a bit bigger. So therefore we can say that hardening of the hot roll 316L can be reasoned with twinning and martensite transformation, so it should be a mixture out of it. But in the end, also the lower nickel content of the hot roll 316L may lead to a higher transformation affinity from austenite to martensite. If you take a look at the Scheffler diagram, you can see that with a lower nickel content, we're moving closer to the austenite and martensite area. One thing I have to mention in the end, for the EBSD measurements and also for SEM measurements, we can only see a small picture of it. So we cannot really say that it stands for the overall material. So that's why we conducted a few weeks ago some measurements at the electron synchrotron in Hamburg to do in situ fatigue testing. And there we could measure the dislocation density and also the phase transformation to take a look at the overall structure, because we were able to take a look at the whole measuring area during testing. It was quite nice to see. So keep that in mind. Yeah, that was it. Thank you very much for your attention.
We have time for one question, yes?
Okay. So, thank you for a very nice presentation. Concerning your latest point on how it's difficult to measure the amount of martensite with EBSD, so why not to try just a simple magnetic saturation method like ferrite scope?
I did that actually. Let me show you. I measured that here. So here I have a martensite content or ferrite content of 11.5%, and here I have 0.3% after 2.5% strain amplitude. So yes, I mean there is a transformation happening, because before loading we had only 0.3% here and 0% there. But I would like to see it in the micrographs as well to be really sure. But you're right. Yeah. Thank you.
Okay. So thank you so much again.